Hello and welcome to the third part of the lecture for topic 2 for week 8. This will be some questions relating to hydraulic lifts and buoyancy and Archimedes' principle. So we'll jump over as usual to our question slides and we'll discuss some of these questions. First question, hydrometer or hydrometer. A hydrometer is an instrument designed to measure the specific gravity of a liquid. It is a weighted glass tube with mass of 45 grams, length of 25 centimeters, and a cross-sectional area of 2 square centimeters. Where should the 1.00 mark be made? Right, so remember that the specific gravity of a liquid is the ratio of the density of that liquid to the density of water. Right? So what we need is that when it is placed in pure water, perfectly pure water with a density of 1.000, that we have a reading of 1.000 on it, right? So that's what we're looking for, is that when we place it in pure water, it sits an exact value below, it sits at that exact position below the water as per the diagram. The 1.000 is at our water level when this is pure water. If you remember from the question at the end of the last video, we talked about an iceberg in seawater, and I mentioned that seawater has other things in it. It can obviously it's got salt, which changes the density, and then it's got other things, and then temperature and all sorts of other things can affect the density. So a device like this is useful because it allows you to test the density of water at different places by simply dropping it in and reading off a scale as to whether or not the density is greater or lower, or what it is, what that specific gravity is. So as usual with these questions, we'll move to the document camera and we'll have a bit of a think about this problem. So first of all, write down what we know. That's a good way to start, right? So mass is equal to 45.0 grams or 0.045 kgs. SI units are always good. Length is equal to 25 centimeters, 0.0 centimeters, which is equal to 0.250 meters. And the cross-sectional area A is equal to 2 centimeters squared. Now, when you have an area that you're converting into a different unit, you have to remember to change the unit twice. So I'll actually just take a second to remind people of how this works. When you've got 2.00 centimeters squared, that is 2.00 centimeters times centimeters, right? That's what centimeters squared means, centimeters times centimeters. So if you divide that by 100, right, divide by 100 will change centimeters into meters, right? But it only changes one of them. So if we divide that by 100, so it's now 0.0200, one of those centimeters goes into meters, but the other one is still centimeters. We've only done it once. So we have to do it again. Divide by 100, that'll change the other centimeters into meters. Right, and we end up with, I'm going to move to scientific notation now because it's going to be, 2 is in the 4th decimal place if we move it 2 more places down. So it's 2.00 times 10 to the negative 4 meters squared. So just a reminder that you have to divide twice to change a square centimeters into a square meters. Similarly, if you are looking at cubes, if you're looking at volumes with cubic centimeters or millimeters or whatever, you need to do the conversion 3 times because you've actually got that unit 3 times in your value. So that little aside tells us we have 2.00 times 10 to the minus 4 meters squared. And what is the question asking us? Well, it's asking us where we want to put our marking on the hydrometer. So here's our hydrometer. We've got total length 25 centimeters, and we're asked to find some value. What distance up the hydrometer should we put our 1.00 specific gravity mark? So what that means is that we have to think about our floating equation. Remember that when something is floating in our water, the ratio that we have is that the volume of our object is equal to the ratio of densities times the volume of displaced fluid. Right? So if you can remember that equation, right? That equation, I'll write it out actually, just hopefully you'll remember this one. Volume of displaced fluid is equal to the ratio of densities of the fluid, I don't need the D there, but same difference, times the volume of the object. Now, obviously, you can do it either way. If you put the ratio on the other side, it would just be flipped up the other way. So it depends which one you're looking for. What we're looking for is the volume of the displaced fluid, because we want to know this bit. We want to know how far down we need to be. So what we need then is the density of fluid and object. We've been told the volume of the object. We do actually have the volume of the object. We have that because we've been given our length and our area, and we know that a length times an area will give us the volume. So that's fine. So we actually know the volume of the object, but we don't know the density of the object yet, but we can calculate that too, because the density of an object, density of the object is equal to the mass of the object over the volume of the object. We've been given the mass, and I just said we can calculate the volume. So mass of object over the length times the area. That will give us our density of our object. So we know the density of the object. We know the original volume of the object. The volume of the displaced fluid is what we're looking for. What's this one? What's the density of the fluid? Hopefully you're all remembering that the density of our displaced fluid is 1, right? It's pure water, because that's the point of the question. We're saying, if we put this in pure water, how far down will it go? Because that is where we're going to write our line for 1.00 in our specific gravity markings. So we know that. We have a formula for the density of the object and a formula for the volume of the object in terms of things we know. I'll just write that out to be perfectly clear. All right. So that's what we have. And what we're looking for is this length here. So what I'm going to do is I'm going to write, see I've got x defined as the distance from the bottom up to here. The volume of our object then, remember that we've still got our area is still the same, 2 centimeters squared. So the volume displaced fluid is going to be A times x, whereas the volume of our object was L times A. We're going to have our volume of our displaced fluid is equal to x times A. So now we actually have an equation that's got everything we know apart from x. And so you could, as I always say, you could do this calculation by going and figuring out all of these different things, determine the volume of the displaced fluid. Or actually, no, you can't do that one because that's what we're getting at the end. But you could determine the density of the object. You could determine the volume of the object. You could then use that with this relationship here and the density of water to get the volume of the displaced fluid, and then you can put that into here with your area and figure out A. So you could do 4 or 5 separate calculations, or you can just do one big calculation, one rearrange of algebra, and then a big calculation. So we're going to replace everything in this equation with these terms that we've got here. So we have x times A is equal to the density of our object, which is this equation here. So m object over L times A, divided by the density of the fluid, which is, that's just given, it's the density of pure water, and then times the volume of the object, which is L times A. So what have we got out of that? Well, we have, we've actually got A's we could cancel all over the place. I'm going to cancel this one and this one. And then I'm going to cancel this L and this L. And we're left with x is equal to the mass of the object over area times the density of the fluid, which is the density of water. And we get, so the mass of the object was 0.0450 kilograms, divided by the area, which was 2 times 10 to the negative 4 square meters. times 1,000 for the density of water. That's still got 0.00. It is 3 significant figures. I've just left it off for ease of writing. And now we can do that calculation. So I will grab my calculator, as I hope you all have, and we'll see if I get something that is appropriate. Divided by 2 exponent -4 times 1,000. And I get 0.225 meters. So that tells me that in this scenario here, X is 22.5 centimeters. And that's all the question is asking us. How far up from the bottom should our marking be? And so at this point, we can stop and say, well, does that make sense? Well, yes, it's not all the way up the device, right? It's not all the way up there. We can certainly make a marking on there. If we had some X value that was greater than 25 centimeters, then that would mean that it's sinking, right? It's gone, and that's not really possible for us to have a marking that's above the device. It wouldn't be useful. And likewise, if the value was too low, if we got it that was only like a centimeter up, then this device is not going to float, right? If you have a device and it's only a little bit below the surface of the water, then that's not going to be stable and it's going to tip over, and so it's also not going to be useful. So it makes sense that the reading is somewhere near the top of our device so that it sits underwater quite happily. The other thing you could do if you wanted to is actually do one of those intermediate calculations. Do this one, do the volume, the density of the object. And if you calculate the density of the object, then since it floats, we know it has to be less than the density of water, so it has to be less than 1. But since it's floating most of the way down, which is what we expect it to float most of the way down under the water, it should be close to 1. So it should be a density which is fairly close to 1 kilogram per 1,000 kilograms per cubic meter. And I've just realized I've written that wrong in here, times 10 to the 3. Hopefully you all picked that up. I did the calculation correctly though when I put in the density of 1,000. So hopefully if you check that, it'll come out to something a bit less than 1,000, which agrees with what we said, that it should sink most of the way, but then float with a little bit poking out the top. In fact, 2.5 centimeters poking out the top. So as I said, stopping and thinking at the end there is quite useful. You could have also thought at the start when you look at this picture. If I jump back to the question, to the slides, now this is actually the answer one. If you look at the picture, you can see that it's most of the way up, so you'd expect it to be most of the way up. Now I did actually do a slightly different method in this answer slide that you'll see when you read that, so do have a think through that. You may not have approached it exactly the same way I just did in my calculation. It's almost a bit of a shortcut that I take in the slides, so take the time to read through that and follow along. Bonus question. This is a question I'm not going to answer. It's for you to think about, discuss with people, make a post on the forums if you want to check your answer with some other students. But it's just one for you to think about. Hopefully won't be too difficult. You have everything you need to be able to answer it. And the question is, should the markings above the 1.00 marking represent higher or lower fluid densities? So here's our 1.00. The markings above here, are they higher or lower fluid densities than pure water? And are these higher or lower densities than pure water? So that's the bonus question, which I'm not going to answer, but you can have a think about. Next question, we have a submerged human of mass 60 kilograms and volume 0.05 cubic meters. And yes, that is actually about right for a human, which seems small, but that's about right. Is submerged in a pool of pure fresh water. What is their apparent weight? So this is where you need to remember the terminology apparent weight. So hopefully you can recall apparent weight was the effective weight of an object when it's underwater. So an object that is submerged has a weight force and it has a buoyant force, and the net force between those two is our apparent weight. So that's all we're after. We're after the apparent weight. And so we've been told the mass. So F weight is equal to mass times gravity. That's easy enough. And the buoyant force, is going to be the weight force of the displaced fluid, right? Archimedes principle, just drilling that in, the buoyant force is the weight force of the displaced fluid. We've been given a volume. We've been told, did we get told pure water? Yes, pure fresh water, so pure water. So we know the density is 1,000, and so we have mass times gravity, and for the mass we're going to go with density times volume times gravity, right? Remember, this is something you should all be familiar with by now. Density is mass over volume, so as long as we know two of them, we can figure out the third one. In this case, we've been told the density and the volume, so the mass is going to be density times volume. So hopefully you're all happy with that. So what we have is that the weight force is mg, the buoyant force is rho vg, so therefore our F net is going to be, again, choose your frame of reference. I'm going to call this one negative and this one positive, even though when we write out the answer, we'll just give it as a value because it's an apparent weight and we just always know that it's downwards. So the apparent weight is the buoyant force is going to be positive rho vg minus mg. And so you can put those values in your calculator. 1,000 times 0.05 meters cubed times 9.8 minus the mass, which was 60 kilograms times 9.8. And hopefully what you get is negative 98 newtons. Negative 98 newtons. And that means that our apparent weight is simply 98 newtons. So fairly straightforward question, just a fact of remembering the definition of apparent weight. That was the goal with that one. Right, next question. I believe this is the last one, but I can't be certain. Question is floaty block. We have a block that is floating 3/4 submerged in fresh water. What is the density of the object? So this time we haven't been given any volumes, we haven't been given any densities. We've been told fresh water, so actually we have been given one. Indirectly, we've been given the density of the liquid as 1.00 times 10 to the 3 kilograms per cubic meter. And we're asked, what is the density of the object? And then there's a second part to the question which says, if we take that object that was floating 3/4 submerged in fresh water and put it in an oil which is half as dense as water, what does the object do? So a few things to unpack in this question, bit of stuff to think about. First thing is to write down what we know, and that is that if it's floating 3/4, right, 3/4 submerged, then that means that the displaced fluid volume is equal to 3/4 of the object volume. Right? So that's what we've been told. We've also been told that the density of the fluid is equal to 1,000 kilograms per cubic meter. So now, how can we figure out the density of our object? Well, we've got this fraction here is what was given to us. And if you remember the equation for floating objects, volume displaced fluid is equal to the density of the object over the density of the fluid times the volume of the object. Right. Again, one of those equations that hopefully you'll remember. We'll always give you equations, or you'll, in the case of this semester, you'll be open book tests anyway, so you can always look these up. But remembering this equation isn't generally too difficult anyway. And if you look at this and look at this, then hopefully you can spot that we already have rho O over rho F is equal to 3/4. Right? We don't need these two volumes because we're told this ratio of 3/4, and that's going to be the same as the ratio of our densities. All right, so just by comparing those two formulas, we can see that rho naught over rho object over rho F has to be 3/4. And of course, we know the density of the fluid is 1,000, so we'll times both sides by 1,000, and we get that the density of the object is 3/4 of 1,000, or 750 kilograms per cubic meter. So if the volume of the object is 3/4 submerged, the object is 3/4 submerged, then the density is 3/4 that of water. That's the first part of the question done. And the second part is actually a very simple question. Now that we know the density of the object, and they tell us the density of the fluid because they said it is half as dense as water. Right? So the density of the oil is equal to a half of the density of water, which equals 500 kilograms per cubic meter. And we now have an object that has a density of 750 kilograms per cubic meter placed in a liquid which has 500 kilograms per cubic meter density. Therefore, it will sink. Right? The object is more dense than the fluid. The object will sink. So that's the answer to part 2 of the floaty block. And there is actually one more question, which I will jump over to now. We have a sunken statue. A statue with mass 70 kilograms and volume 3 times 10 to the 4. That should be a 4 up in the exponent. 10 to the 4 centimeters cubed sits at the bottom of the ocean. Seawater has a density of 1,025 kilograms per cubic meter. So you might recall we've seen different densities for seawater. In this instance, we're being told that density. If we weren't told one, we could go and look up different reference tables. But as I already said, it does vary. So if you're given a value, make sure you use the given value. And the question is, what force is needed to lift the statue? So to lift something, we're not accelerating upwards. To lift something, we're just moving upwards at a constant speed. That means that we have no net force. So what we need is for the net forces to balance out. And if this object is underwater, then it will have an apparent weight. The apparent weight is going to be given by our buoyancy force and the actual weight. And that's all that's going to be on it. So once it's lifted off the floor of the ocean, the only things on it are the buoyant force and the weight force and whatever force we apply. And so that has to equal the apparent weight. So we'll just jump back over here. So as I've been saying, if you've got the sea floor, you've got your statue. I don't know if the yellow will show up very well on this camera, but you've got your statue. Then this statue has an apparent weight, right, which is given by the weight force, the buoyant force, and some extra force that we're applying, which I'll call F lift for now. And if we're moving with acceleration equal to 0, because there's no need for us to accelerate it upwards, we're just trying to move it upwards with a constant velocity, so we don't need any acceleration. That means that our net force is equal to 0. And so the net force is the sum of all of these. The net force is equal to the buoyant force plus the lift force minus the weight force. Right? Weight is downwards. So how do we figure out all of these things? So let's take a little detour and write out all the information we've been given. We've been given the mass is equal to 70 kilograms. We've been given the volume. Volume of the object is equal to 3.0 times 10 to the 4 centimeters cubed. Centimeters cubed, so we need to divide by 100 3 times. So it'll be 0.030 meters cubed. Double check that calculation for me. I just did that in my head. It's very possible I've done it incorrectly, but again, remembering you need to divide by 100 3 times to change every one of those centimeters, because that's the same as centimeters times centimeters times centimeters. You need to change each one of them into meters, so divide by 100 3 times to get our volume of the object in meters cubed. We're told the density of the fluid is 1,025 kilograms per cubic meter. And that should be all we need, I think. So let's go back to our equation now. The buoyancy force, this buoyancy force is equal to the weight force of the displaced fluid, which is equal to the mass of the displaced fluid times gravity. And the mass of the displaced fluid from our density equation, as I said, get used to that, you'll be using it a lot. Mass of the displaced fluid is going to be the density of the fluid times the volume of the object times gravity. So we know that one. The lift force is what we're trying to figure out. Remember, the net force is 0. The lift force is what we're trying to figure out. And the weight force is just equal to the mass of the object times gravity. So we've actually got everything we need now. We can plug it all in and figure out our result. So we have that 0 is equal to rho F V naught V object gravity, that's the buoyant force, plus F lift, that's what we're looking for, minus M of the object times gravity, mass of the object. I'm just adding a little O in actually, because we have now got a massive displaced fluid in there. So I'll keep an O just to be clear. So we've got this as our equation. We're looking for FL. So the lift force is equal to, if we move this over this side and this over this side, but I've actually flipped them. So this over this side gives us M naught G minus the density of the fluid times the volume of the object times gravity. So again, you'll notice that I'm rearranging the equation and I'm going to do a single calculation. If you prefer to go through and calculate the buoyant force, calculate the weight force, take the difference of them, and then that gives you your lift force, that is acceptable. But as I've said multiple times, that does introduce room for error, whereas this way you can just rearrange everything into a single calculation, and it removes any chance for A, typing the wrong equations in to the calculator, or B, rounding errors that do arise. So we can now do one calculation with this, with these. So 70 times 9.8 minus 1025 times 0.03 times 9.8. And hopefully you all get out the same value as I do, which is 392 newtons. So you need to lift 392 newtons. In the answer slides, I have again taken a slightly different approach. I try to do things a little bit differently where there are multiple ways to think about it. Here, what I've done is I've assumed we have the lift force and our net force is going to be 0, and then figured out what that lift force is. In the answers on the slides, that is, I have not had a lift force, and I've said before we apply the lift force, what's the net force? Because when we apply the lift force, we're going to have to equal that net force. So it's the same idea, same concept. I've just done the description slightly differently. And that's just to reinforce that there is no one correct way to do all of this. But regardless of the approach you take, you should get that same result out. So hopefully you're able to follow through all of that. There's plenty to practice. There's quite a few formulas to get used to, and we'll only be introducing some more next week in the next lecture tomorrow. So I'll see you at the Zoom meetings and or at the next lecture. Thank you.